there are many instances that we might need to work out the area under a curve using integration, but there's some difficulty. So if we do want to work out this area, let's say this whole area under this curve between x equals a and x equals b, so we can write this area here as the integration of my function f of x between a and b. That's what we want. Now, why might we not be able to actually calculate this? Well, the first possibility is that actually my function f, I can't integrate. None of my methods, none of my standard integrations apply, and I just can't do this integration. The other possibility is I don't actually know the function. So I don't know a mathematical expression for the function. What I might know is this function at various points. So for various different inputs, x, I might know the value of the output, f of x. Let's take a really simple example. Let's imagine I want to work out the area here, and all I know are the values of my function at the value x equals a. So let's call it f at a. So the function f evaluated at a, I know that value. And I also know it here at x equals b. So across here, I know this value of y, the output, f at b. How can I really roughly work out the area underneath this curve? Well, what I could do is simply take this area, the area of this rectangle. Okay, so the area of that rectangle is pretty easy to work out. Let's call this distance here between A and B. Let's call this h. So in this case, it's B minus A. I know the height of my rectangle. It's this value f of A. So the area of the square, let's call it A1 for this square, this first bit of area. Well, it's just this width multiplied by the height. So it's h times f of a. Okay, and you can see this is a really bad estimate. Well, probably pretty bad, depending on what the function looks like. But unless the function is flat, this is going to not be a good estimation. What we could add in is the area of a triangle, which is formed by going from this point here and this point here, 2 points on our curve, and I'm going to add in the area of this triangle. Okay, well, this triangle here, let's think about this area. Let's call it A2. Well, it's a half base times height. That's the area of a triangle. So that's a half times the length of the base. That's h. Times its height. What's its height? The height of this is actually the difference between f at b and f at a. Okay, so adding these two areas gives me an approximation for our full area. If I add these two up, what I get is this approximation for my area, which is a half h fb, this half h fb, and then actually I add on h times fa and a half h times fa subtracted. In fact, this turns out to be a half h times fa. Okay, so what I've got now is an approximate area for under this curve. The reason this is called the trapezoidal rule is because this shape here now, the rectangle and the triangle, is a trapezium. Okay, so that's a very simple example of just taking one shape there between A and B. What if I now subdivide this into lots of strips and do the same thing for each strip? So each strip now has a width here, which is actually, depending on how many strips I've got, let's say I've got n strips. The width of this strip is b minus a, the total length here, divided by n, where n is the number of strips. What do I need to work out each of these areas of each trapezium? I'll actually need the values, all the different x values. I need the value of the function evaluated at every different x value. So let's say I've got these points here. I go from x1, x2, x3, x4, etc., all the way up to this point here. Now there are n strips. That means there are n plus 1 points. I need the start and finish of every strip. So the final one is the point xn plus 1. And at each of those values, I will need the value of the function. So I need f at x1, f at x2, all the way up to f at xn plus 1. And then I can form the little area for each of these trapezia. I use the same formula, and I can add them all up and get a really good approximation to my area. The final formula, what you're going to do now is add up all of these values of my function f. The final formula then is that my area is approximately a half times this distance, this width h, which is now a much smaller width than the original one, multiplied by a whole load of functions, the function evaluations at x1, x2, etc. The key here is that the very first strip uses f at x1 and f at x2. The next strip uses f at x2 again and f of x3. All the ones inside are actually going to be used twice. So the final formula adds up f at x1 and then twice all of the ones f at x2 all the way up to f at xn, and then finally adds on the single value f at xn plus 1. The two endpoints at x1 and xn plus 1, these two endpoints, which are actually x equals a and x equals b, they're only counted once. The rest of the points are actually added in twice. So this is our final rule. There's quite a lot of work to get there. I've got to evaluate my function at lots of different points. I add them all up, and I use this formula, and this is the trapezoidal rule. Let's do an example of using the trapezoidal rule. Okay, so here I'm asked to work out or evaluate or at least approximate this integral here using the trapezoidal rule with 4 strips. I always like to do a sketch of this. So what we're asked is to consider the graph y equals e to the x, this thing in the integral here, and I'm effectively wanting to integrate and work out the area underneath that graph between x equals 1 and x equals 2. That's the area I want. I'm going to approximate that by creating 4 different strips and working out those areas. So if I create 4 strips between x is 1 and x is 2, so I'm looking at these 4 strips here, and each of those strips I'm going to approximate with a trapezium, which is almost, from this sketch here, it should be very accurate form of this integration. And what I need to work out is a few different things. I'll need for the formula, I'll need the value of my function at each of these points. And I'll need to know the thickness of these strips. Well, the thickness of the strips is relatively easy. I'm integrating from what we might say is x is a to x equals b. So a in this case is 1, b is 2. The thickness of the strip, h, is b minus a over the number of strips. B minus a is 2 minus 1, divided by the number of strips is 4. That's a quarter. Well, you could have seen that really just by thinking about this graph here. It's a unit length of 1 divided by 4. The strip width here is going to be a quarter. So h is a quarter. And my different positions now, the x positions, x1 is just the point 1. x2 is the next point along, and that's 1 plus a quarter, 1.25. x3, x4, and the final one, x5, Okay, there are n+1 positions. If you look at this, there's 1, 2, 3, 4, 5 values of x. So these I just add on a quarter each time. The final one should be the last point I want to integrate to, this upper limit, x equals 2. For each of these values, I'm now going to work out the function evaluated at those values. So I'm going to form a little table where I evaluate f of x. Let's just do the end points first and then do the middle points. So I want f evaluated at x1 equals 1. So all I do is I take e to the x and I substitute x equals 1. So this is e to the 1, which numerically is 2.718282. Okay, I've used quite high accuracy here because when we're doing this kind of approximate integral, retain as much accuracy in terms of the decimals as you can. The very final one here, I'm also going to do, this is e to the 2. It's just e to the x at x equals 2. And just writing down the decimal form of that. 7.389056. And then I'll do all the intermediate ones. So this is e to the power 1.25, e to the power 1.5, etc. And I just use my calculator for all of these, and here they are. There are all the values of my function. How do I combine all of these using the formula? Well, the formula, if you remember, tells me that my area is approximately equal to h over 2 times the function of x evaluated at x1, then twice the function at all the midpoints, so x2 all the way up to f at xn, and then I add on the function at the very end point, n plus 1. Okay, so here, my end points are this value here, and this value here, and the rest are going to be doubled. So I need to do the sum of these and then double it. So I put all this into my formula here, and in the end, I get an approximate integral e to the x dx is approximately equal to 4.695076. I retain my decimal accuracy all the way down to the end, and then this is a relatively good approximation, it turns out, to this integral between 1 and 2.